Okay, so our last speaker for this session is Natan Argaman from Nuclear Research Center of the Negev. Thank you.
Thank you. How do I full screen it on PDF? You probably. Okay. So I want to thank Lev and the organizers. I want to appreciate your courage for trying to create a consensus in this type of crowd. It's not going to be easy. I'd like to tell you about future input dependence. This is a form of retrocausality, but the retrocausal word means different things to different people, so we try to have a more accurate description of what we're talking about. It's less about philosophy, more about concrete models in physics. And I would like to suggest that maybe it can be used as an interpretation of quantum mechanics rather than as a model, as a theory. So I will start and end with many worlds interpretation. I will talk about the arrow of time. I will present a specific model developed by Schulman. And then I will pause for a discussion, actually, so to make sure that people actually appreciate this model. And then I will present some ideas for the continuum and so on. Okay, so many worlds, there are lots of features. I will not repeat most of them. I'll just mention that it uses the Newtonian schema. So there's a Hilbert space wave function or array and some dynamics oriented towards the future, which is, that's part of the many worlds interpretation. The wave function itself is reified. There is determinism, which is seen by some as an advantage. There's the claim of locality, but this locality is a bit in question. And I will present alternatives and you know, Vali Alori already tried to present some alternatives, but this has something to do with the arrow of time, which we have not discussed yet. So it's important to discuss the alternatives. Now, when people talk about locality in quantum mechanics, people usually think about Bell's theorem. So it's a problem here. I don't want to give a talk about Bell's theorem. I have a long talk about that together with Ken Fortin, my collaborator. But the bottom line from Bell's theorem, from the whole discussion, is that even if you cannot have a description that is locally causal, which entails this separability, it still does not have non-local signaling. So this issue of locality is not a yes-no question. There are various criteria for locality, and some criteria are met, some are not. Yeah, so the bottom line for Bell was, in fact, that there seems to be some tension between quantum mechanics and relativity. But what he was actually discussing is relativistic causality. So the issue of the causal arrow of time is also one of the assumptions. And in fact, Bell's theorem rests on these three different pillars. This is a 19th century issue, the arrow of time. And the arrow of time itself is also not a yes-no question. There are several arrows of time. And a theory or a model can violate one of them without violating another. And in particular, what I'm saying here is that retro signaling, you know, the grandfather paradox and so on, we know we cannot retro signal, but we don't necessarily know whether we will or we will not have future input dependence in a model. So I'd like to discuss mathematical models, and I would like to discuss mathematical models that describe irreversible physics. Actually, this picture was part of a presentation. The previous speaker used the same picture of the Schrödinger cat, but I removed the Schrödinger cat from the picture because I don't want to discuss things which are too complicated for a concrete mathematical model. So I don't believe we will have models of cats or agents or universes in all their detail in an exact science sense. It will be too complicated for us. I'm talking about simple physics models. They all have controllable inputs. They all have observable outputs. They have hidden variables sometimes. And these are important for continuity. So if you have some kind of signaling in your box, so Schrödinger put the detector, the measurement, signaling, entropy, all these things exist and can be described in physics models and are usually often described in physics models. And all these models require some kind of irreversibility. They require a past hypothesis. And we actually know from the 19th century how to introduce that into our models. We either fix the initial conditions or average them in a way that reflects the idea of molecular chaos, but always towards the past. The molecular chaos exists in the past and not the future. It affects the past initial conditions, not the future final conditions or future boundary conditions. And so we know how to deal with this. And it's also known how to deal with this in quantum mechanics. Feynman and Vernon, Caldera and Leggett in the condensed matter context, averaging over the initial conditions of the environment is known, and it does the job. It allows you to describe signaling towards the future and prevents you from signaling towards the past. Okay, so with this, I want to come to an example because I think the best way to think about this is to consider an example. So Schulman already in the 90s developed a specific model for a photon that passes from between two polarizers, and say it passes both of them. So there's a polarizer at some angle, there's an analyzer at a relative angle, delta theta, and the photon is known to pass through. In standard quantum mechanics, the polarization of the photon along this line is presented as equal to the angle of the polarizer. And then it changes abruptly or maybe splits into two possibilities when you have the measurement here. But Schulman proposed a different kind of model, and maybe our next model in physics is going to be similar to this. In this model, there's a random walk. So the overall change in the angle is due to lots of little kicks. And the distribution of each kick has to be Lorentzian or fat-tailed, so as to produce a Levy flight. Otherwise, this description turns out not to be interesting. So please accept this as one of the assumptions of the models. This gamma is the overall width, the sum over all the Lorentzian widths of all the kicks. And the idea is not only to take this overall Lorentzian, but to impose a constraint so that the overall change in angle has to be equal to delta theta up to, say, 180 degrees, or maybe 360, maybe minus 180, and so on. So when this constraint is imposed, it of course affects the whole description. So at earlier times, some of the paths which were previously just the distributed Lorentzian, now they feel this future input. This input from the future, this angle, affects these paths, and only some of them are now probable. And so this creates a result where your description is time symmetric. The polarization of the photon in between the two polarizers depends both on its initial and the final angle. And if you want to really get a strict Levy flight, you have to take the overall angle, the overall width, gamma, to be very small. In this case, with overwhelming probability, there will be only one kick, which is of order delta theta. The other kicks will all be very small, of order, the individual gammas of the little kicks. And if you have two kicks, which are of order delta theta, there will be, that will be down by a factor of, another factor of gamma. So that will be with relatively very low probability to occur. Okay, so until this point, this is just a neat description, but it doesn't have any quantitative doesn't give any quantitative prediction. What Schulman said was, in fact, we have to impose either this possibility that the photon actually passes the analyzer, or that it is absorbed or reflected, and that the polarization is essentially discovered to be perpendicular to this angle. So you add pi over 2. Now, to develop this quantitatively, you have to sum over all these possibilities. This is what you have if you look at, if you look at this and take gamma to 0, the probability you are left with is proportional to 1 over delta q squared. So you sum over all the different values of n. It turns out that this is just equal to 1 over sine squared delta theta. It must be periodic with period pi, and it must diverge as 1 over delta theta squared when delta theta is small, so this makes sense. And now you can add the two possibilities. This is one possibility, this one. The other one is shifted by pi over 2, so it's 1 over cosine squared delta theta. So when you now take this and impose that one of them happens, you have to normalize the overall distribution, and then you get just Malus's law. You divide by this, you get cosine squared delta theta. So you get the correct, the one we know from quantum mechanics or from experience, the correct prediction for the probabilities of these photons from this simple exercise. So this is a very interesting model, I think. It is continuous. It's future input dependence. It doesn't have any retro signaling. It's stochastic. It requires an all-at-once approach, so you need to take a block universe-like approach and think of the final condition as being defined even when the photon is along the way. And you could ask whether it explains things, whether it solves the mysteries of quantum mechanics or eases them. Is this a good starting point for an interpretation? And you find that if you think of just repeating measurements, so imagine you have 3 or 4 polarizers in series, and you think of the Leggett-Garg inequalities, well, if you just obey the Malus law, then the Leggett-Garg inequalities, you get just the violation of the Leggett-Garg inequalities which you expect. So that's nice. And if you want to explain Bell locality, you just need to take 2 of these photons emitted by a source and require that their initial polarization is equal for both photons. Because what you get in this type of description is that in this case, it's enough to have one significant kick along one of these photon paths. And that is the dominant possibility. So the polarization of the photons immediately after they're emitted from the source or even at the source adjusts itself in a way that depends on the future input. So it just fits either this input or that input or perpendicular to it. And in this way, the Bell inequality violations are precisely reproduced because they're that similar to Malus' law that it's essentially the same thing. And this, if you're willing to accept this approach that, you have some violation of the arrow of time, but only for these hidden variables. So, only the polarization in between here, which is not measured, can depend on future inputs. So you cannot have any signaling to the past. This is enough to demystify much of what you would see here. Of course, this is a very limited model, but let me just stop here for a minute and see if there are any questions. Okay.
Does the kick have to happen in between the polarizers, or can the first polarizer introduce the kick by, for example, the motion of its molecules, or maybe it's the vacuum fluctuations that introduce the kick?
Well, it could be vacuum fluctuations, and then you would think that they exist all along the path. So there is no, once you remove the constraint that the future does not exist and you cannot rely on anything from the future, and you say, yes, we are allowed to build a model which is a block universe type of model and which has whatever happens in the future and these boundary conditions for the physics we are discussing, these boundary conditions are known to us and can affect the earlier description. Once you allow this, there are many ways to do it. So I'm sure that what you're saying is also a possibility. In fact, in our longer paper, we have several toy models to present this.
What do we mean by the probabilities here? I thought at one point we said we're fixing the final outcome. We're fixing the we're fixing whether it ends up passing through or reflected and conditioning on that. So that would mean that we should treat that as definitely happening, right? And then but then we're also giving probabilities for it. So I'm just
Right.
confused
So
about that.
yeah. This is an important point. The idea is to have expressions of this type. This is, again, for Bell correlations. You have some inputs, you have some outputs, and quantum mechanics already gives us, the standard applications of quantum mechanics, we know what the input variables are, we know what the outcomes, these are settings of the measurement apparatus, and these are outcomes of the measurements, and we have to reproduce this type of expression. So the idea is that the overall description will produce something like this, but it's allowed to produce it with something which has additional variables which will fill in what is happening along these paths. So, yeah.
I'm just asking what we mean by when we say probabilities. What are we conditioning on? When we say that that with the initial we have initial polarization, let's say vertical, and then it either passes through the analyzer or it doesn't. But
right. We're I guess in this case we're conditioning on the initial polarization, which is an input, and the final angle of the analyzer is an input. But whether the photon passes or not is considered to be an output in this case, in this simple case. Right? So the probability is just Malus's law. So this is the outcome, this is the overall probability for having the photon pass the second analyzer. And there are also probabilities for all the individual picks, which are obtained from this rule of, imposing these Lorentzians, and then at the end, when you have the overall view, you normalize, you impose the constraints, also these constraints, and then you normalize what you receive. So you don't have, the initial probabilities are no longer those that are obtained after normalization.
Okay, so we're conditioning on that one of those two outcomes happens, that it's either a whole or a half multiple of pi,
right,
and not something in between.
Right. Yeah. All these paths are sensitive to the final conditions. So those that reach this analyzer without reaching either this angle or perpendicular to it will be wiped out from the distribution. Yeah.
And then conditioning on that, then we have leftover probabilities.
Yeah.
Okay.
A few years ago, Rolf Kastner published a book on the transactional interpretation of quantum mechanics. Are you aware of the book? Did you read it?
Well, I'm aware of the book, but I did not read it. I heard the talk she gave recently.
I recommend it because what you are doing, you are trying to invoke breadth causality, which is important. You are trying to avoid backward singling, which is important.
Yeah.
She quotes me in an experiment which was not published yet, but which shows that a kind of backward singling can inflict such models. It strains them. It doesn't create a full paradox, but it strains such kind of a model.
Okay, great. So I would be very happy to discuss this with you. But I do want to stress that the type of approach she takes, Kramer's transactional interpretation and the two-state vector formalism that was also mentioned already, these things not only use retrocausality, but they also use the wave function, and they're sort of forced to reify the wave function in some sense. And what I'm aiming at is models that do not reify the wave function. So the wave function is analogous to a distribution like a probability distribution function, which evolves deterministically if you have the diffusion equation. But then if you actually have a random walker inside, there is some microscopic degree of freedom which has a random walk, and you flash light on it and you see where it is, then the wave function collapses. And what you take to be reality is only the random walk, not the wave function is just a mathematical prescription for following the probabilities. Sorry? Oh yes, I'm not following Schulman on this. So Schulman developed many things in his book, and I'm only using this single thing, which is the Levy flight model, which I've just described. So I'm suggesting something that's slightly different. Even my collaborator, Ken Wharton, actually wants to have eventually deterministic models, and I want to emphasize stochastic models. So let me continue to that. I think I still have quite a few minutes, and there will be more time for questions at the end. Okay? I end by 10 past, is that it? Okay, I mean, you want to have lots and lots of discussion. Yeah, okay, so let's see what I will do. So, yeah, so let me skip this and go right to this. So the idea is if you want to generalize this model, this is just a toy model that describes just a very limited possibility, a set of contexts. And I would like to describe, I would like to get some interpretation for the whole of quantum mechanics or maybe the whole of quantum field theory, because we know that relativistically we do have quantum field theories. And so I mentioned that this model is stochastic, it's future input dependent, it has hidden variables. What if we consider a field, okay? So imagine that there is a field of hidden variables. Maybe this is the electromagnetic field, so maybe this is a vector potential or something, but I'm talking quite generally. I want to describe the probabilities, the rules for these probabilities of the different configurations of the field. And the field is affected by many inputs. So these inputs represent a source at some point, which is maybe active at some time, and then afterwards and before that it still exists, but I've sort of denoted it by these lines, broken lines. And there are maybe beam splitters and detectors and so on and so forth. And I want to have continuous action, which means that there is some kind of locality, but I have to generalize Bell's condition for locality to situations which allow for future input dependence. So Bell, in his very definition of locality, he talked about local causality. It's not symmetric in time. It depends on assuming a strong arrow of time. And I'm going to, I use this continuous action to represent this type of locality which generalizes Bell's locality to future input dependent models. I'm going to assume that there is some stochastic noise. Maybe, H bar is going to be relevant. So maybe H bar omega for each mode of the electromagnetic field or whatever, like in Nelson's stochastic mechanics. And I'm going to impose the past hypothesis. So I'm going to impose that somewhere back in the initial conditions, things were fixed or average over as in the past hypothesis. Now, what would happen in this type of model? Now, the rules are to be defined. I don't know the rules yet. I've tried to come up with some rules, and then you might get signaling backwards in time, which is bad, and so on. So I'm not sure what the rules will be, and maybe I'm not clever enough to see them. But I hope that there can be such rules, and I hope someone will be clever enough to identify them. And then, but I can think about these generally without imposing this specific rules. So the point is that these modes, there will be some of them which behave macroscopically. Some of them will, H bar will be negligible compared to whatever is happening here in these modes. And these, because of the past hypothesis, will only signal to the future. So anything that happens, imagine there is a pointer here and the pointer points at some angle, this will be made available to the future immediately. So if there's a click in a detector, this information will affect everything. On the other hand, the microscopic values of the field, the ones that are sensitive to high frequencies, which are multiplied by h bar would be too high an energy for this system. The fields don't contain that amount of energy. The fluctuations will be too strong, and if you try to capture such a degree of freedom, try to measure it, in the next moment it will fluctuate to something else. A reliable measurement cannot be affected. So, and of course, in this type of description, you will have also mesoscopic degrees of freedom. So there will be, as for, when you think of an entropy of mesoscopic system, we know that, the law that entropy always increases is violated somehow, and, it's a very low probability the larger the system is. So this type of model would supposedly give this. And now detectors would need additional variables because you would need to describe what's happening within the detector and then coarse grain over that somehow, or maybe that would be your pointer. Repeatable measurements would be perhaps limited to things which are conserved because you want to avoid all these fluctuations, you need some conserved quantity. And there are many, many other things, and most of this would be hand waving.
The idea was to finish slightly later. Anyway, I want to kind of general question. So,
okay, yeah, go ahead. We want to have discussion, fine.
Let's say your theory is succeed. In which sense it will be better than quantum mechanics? Or the whole idea is just to avoid multiple words? This is your exercise? Well, why do you do this?
So I think that the standard approach, let me come to my concluding slide and then it becomes clear, okay? So the many worlds interpretation, we talked about it. In this type of idea, even if I cannot work out the theory in detail, it's clear that it would be a Lagrangian schema, a block universe approach. The wave function would be taken to be epistemic, so it doesn't describe the individual fluctuations, it's only the information we have about the fluctuations according to this view. There is stochastic noise everywhere here, and it has continuous action. So the locality that Bell looked for is actually here, whereas I think that's the main problem. You agree that the many worlds is not separable. A world, you said, the world is a non-local object or a non-local concept. Here, you don't need any non-local concept. The whole thing is continuous. There's no action at a distance at all. There are no concepts that skip over.
There is no action at a distance in many words too, but it's not separable. But so you say stochastic is better than deterministic, you believe, and you say that locality, you're saying that your locality is better, the locality of your theory is stronger in some sense than the locality of many words.
Right.
This is the claim.
Yeah. And then the comparison actually, so let me just come to the very end here. The conclusion here would be that only a single world exists. This is indeed important for me. And which one depends on inputs from the future. Whereas in the many worlds, you do not allow for verifying the future. You don't want to take a block universe approach. And therefore, you have no choice but to verify something that is a construct that is large enough to contain all the possibilities for the individual different settings of future inputs. So that because this is an exponentially large number of possibilities, for many measurements, you would have an exponentially large possibility for all the inputs from the future. And so you need exponentially more information on the present in order to allow for all of this, if indeed the underlying theory describes something that depends on these future inputs.
Just, is it particular outcomes that it's a kind of scheme of Aharonov?
No,
For
not a particular,
outcome.
not a single outcome. It's even when you do give all the eventual inputs, all the inputs from the future, this has stochastic elements in it, so it has a whole distribution of possibilities, and which one is a random event according to this view. Yeah.
I suggest to open the floor.
Yeah. So please.
Thanks. So one, I mean, you touched on this in your last comments. One thing I sort of wasn't clear on is how much confidence should we have that the details will work out in a specific case? I mean, if I have something like, I don't know, the magnetic moment of the electron calculations or chiral perturbation theory or something, is there like a general framework that gives us reason to think that that will definitely be puttable in this frame, or is that sort of like just an aspirational goal?
Well, the whole project here, I mean, as I defined the project for myself, was to find a microscopic model that does use these ideas of future input dependence and continuous action and eventually a single world and so on, in order to get something that is in complete agreement with quantum mechanics. So if it's not in agreement with quantum mechanics, it fails, okay? But now I don't have this nice model that agrees with everything and has all these things. I'm just imagining this as a possibility. And what I think is that it already gives enough information to be regarded as an interpretation of the standard quantum mechanics. So take the standard quantum mechanics, take the Copenhagen interpretation, but just remove from it the fact that there is no underlying world. There is no reality to think about. There is a reality. The reality obeys some rules which we do not know yet. That's the idea.
Okay. So I mean, what I would mean by an interpretation would mean something like if I take any particular application of quantum mechanics, I can describe it in this framework. So if I had, I mean, let it be non-relativistic, let it be the spectrum of hydrogen or something. Is this an interpretation in the sense that you can reproduce the spectrum of hydrogen in it?
The hope is that it would, but that's only a hope at this level, right? So if it disagrees with quantum mechanics on anything, if it's like GRW, it deviates only a little bit, even infinitesimally, it's not the project I'm talking about.
Sure. Okay, but then I guess it sounds like that this is a project to construct an interpretation.
Well, it's a project to construct. Nothing wrong with that. It's a project to construct a reformulation of quantum mechanics. So imagine, path integrals or indeed Nelson stochastic mechanics. It has drawbacks and so on. But if Nelson would not have thought that the future does not exist yet, then he could find a way out of the difficulties he encountered, because one of the main difficulties was entanglement. And here, the simple example of the Bell inequalities and it shows that entanglement is not so mysterious here. And it can, for that I do have a concrete toy model that does it.
I understand, Nathan, that you adhere to a block universe view. I mean, you don't believe that there is a passage of time, the future, past, present exist just like all places exist. You yourself adhere to that.
So I think it's the correct point of view for microscopic theories, for quantum mechanics, and it's also the correct point of view for relativity, and I think the block universe discussions, much of it comes from relativity. But I don't think it's true for us on a personal level. So I'm a condensed matter theorist. I know that more is different. If you have many, many degrees of freedom, the effective theory that correctly describes them on this human scale is not going to be the same. It's not.
Sorry, I don't understand you. We have an EPR experiment. We have Alice and Bob 2-3 days later choosing how to orient the Stern-Gerlach magnets. So according to your model, which I think, because I'm also believe in retrocausation, there should be the decision, the free decision of Alice and Bob, how to align their magnet is already there. And these are human beings who believe that they have freedom of choice. So I don't see how you can, how you reconcile, if you do it all.
You saw this picture where I just removed the cat, right?
You're invoking a kind of space-time zigzag between them, so
Right.
that means that whatever Alice and Bob are going to choose freely is already there, which I'm not arguing with you. All I'm saying, this is a very, very interesting meeting. And here we are discussing the question whether there are other universes in which there are more Lev Weidmans and more Nathan Argamans and, God forbid, more Abshaloms in parallel universe, just as we are doing with little differences. There is another question. Does tomorrow exist? Does the future exist? Does the past exist? Do they all have the same degree of existence? And it would be very nice if some of the next speakers address this question. Do you believe not only that there are many worlds splitting from one another, but also that they are already there, already split in the future? This is, I would say, almost the same question. Are there many universes, many worlds, and are there many times somehow with the same degree of existence? I think that it's a very interesting.
Look, I accept your point of view, but I'm not a philosopher. I cannot really.
It's physics. It's physics, Nathan. It's not philosophy. And it has some.
I remain silent.
Okay.
I don't know.
This is going to be the last question by
Yes, thanks. It is sometimes said in the literature that there are reasons, experimental reasons, to think that the wave function is real. So the basic example is just the phenomenon of interference. We notice that something is interfering indirectly through the scattering pattern that is formed in the device, but we still can infer that there is an interference. And sometimes it is also said that the PBR theorem shows that there are difficulties in interpreting the wave function as the statistical property of an ensemble. Rather, it has to be some sort of a physical state. And so I was wondering if you would like to demote the wave function from the status of a thing, an object, how will you respond to these kinds of arguments saying that it cannot be statistical?
Yes, so these arguments rely on this strong arrow of time assumption, which I would like to, which I think should not be accepted in this context. So one of the difficulties with the PBR theorem, the way that it was presented, is that they assumed the arrow of time, and although that paper was one where they decided to be very careful and to enumerate all their assumptions, they did not mention that they're assuming an arrow of time, and they certainly did not mention which arrow of time they're assuming. So I want to assume the arrow of time for signaling. I want to have a past hypothesis in the theory so that there will be no signaling backwards in time, but I do not think that that's the only arrow of time that has to be discussed. And indeed, these microscopic degrees of freedom, these fluctuations here, they can depend on things that happen in the future. And once you accept that, there is no reason to accept the assumptions of PBR that the state is independent of however it will be measured in the future. And there is no reason to accept even that there is a single photon source, that there is such a thing that we know that it emits a single photon, because heralded photons, when we know that a single photon is emitted, that's a situation where actually there is something inside the box, in the source. There is something there that does the heralding, and in fact, it's an EPR pair which connects this heralding signal with the photon outside, with a single photon. And so these are EPR correlations of a different kind. So maybe they can be understood better when you allow for inputs from the future.
Let us
So-
thank our speaker again.
Thank you very much. תודה רבה.